Hexose nahi, hexa. When I ask carbohydrate, then you will tell hexose. 7. 7. Hepta. 8. 9. 10. Deca. Okay, you have to remember all these things. So here it is 3 carbon containing sugar, or 3 carbon containing monosaccharide. Therefore it is triose. Okay, and the functional group is what? Functional group is what? Only functional group. This is when you say this, then what will you tell it? Aldehyde. No? Functional group is CHO. CHO functional group is aldehyde. If you say only this, then it is carbonyl group. And with carbonyl group, when hydrogen is attached, then it is aldehyde. Okay? So when aldehyde is present in a particular sugar, such a sugar is called what? What is the name? I mentioned on the basis of functional group, sugars are of 2 types, or monosaccharides are of 2 types. What are those types? Here, functional group is aldehyde. And what will you call it? Suma, what will you call it? Aldose. No? If functional group is ketone, then we call it ketose. I mentioned for sugar we use OH. And according to the functional group, if functional group is aldehyde, then it is aldose. ALD of aldehyde and dose of sugar. Okay, carbohydrate or monosaccharide. So it is, what is it? On the basis of number it is, I've said, on the basis of number of carbon, triose, and on the basis of functional group it is aldose. Understand? Now, the thing is, how many isomers of this monosaccharide can be? Spurt. How many isomers? Okay. Yeah.
Based on the chiral molecule.
Chiral. Then Prasad, how many?
2 and
Huh?
2 and 9.
How many? I am asking. I am not asking you a formula. I am asking you total number. Aditi.
4.
4. Sandhana. On what basis? On what basis isomer is determined? What is the basis of it? Actually, the basis of the isomer, how many isomers will be present when it is the concept of chirality. What is chirality?
It should be attached with 4
Different groups. Here, this carbon is attached with H, H, OH and this. This whole is a different structure. So this is different group, this is different group, this and this are the same. 4 are not different, 2 are same. It means three types of group are attached at all the 4 positions. It means this carbon is what? Chiral or not? This carbon is not chiral. Understand? Chiral carbons are asymmetric. It means when all the 4, suppose you put R dash, R double dash, and R. All the 4 groups are different. Such a carbon is called asymmetric carbon, and such a molecule is considered as chiral molecule. Understand? So in the first, when you consider the first, because we start the numbering from the functional group. So this carbon, the valency of this carbon, 1, 2, 3, 4. These two bonds are with the same oxygen. So this carbon is chiral or not? So this is not, this is not. Now see, this carbon is attached with this part, this part, this part, and this part. All these four are different or same. Understand? It means this carbon is chiral or not? This carbon is chiral or asymmetric carbon. Because at all the four positions, different groups are attached. Understand? So generally, when it is asked how many, they will give you a structure and will ask the number of isomers. How many isomers will be present? Now, Asad, you were telling number of isomers is equal to 2 to the power n. N is equal to number of chiral carbon or asymmetric carbon. Okay? Abhishek, now you tell me how many isomers you will get from this. 2. Okay? Because n is equal to 1. So 2, if you put 2 to the power 1 is will be 2. So as you know, it is aldose and its another is ketose, and ketose is dihydroxy acetone. It is isomer, you can see. CH2OH, CH2, CH, CHOH, C double bond O, and CH2 dihydroxy CH2, CH2, CH2. Okay. This is your dihydroxy acetone. If we break it, CH, OH, C double bond O, C, OH. This is, if you see, molecular formula is the same, but structural formula is different. Here the functional group is aldehyde, here the functional group is ketone. When a molecule of glucose breaks during glycolysis, from 6 carbon compound it breaks into 3 carbon containing compounds. One is glyceraldehyde and another is dihydroxyacetone. Because at that time fructose 1,6 biphosphate is cleaved, and then there is formation of glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Okay. Now one more thing is here. Generally, when phosphorylation occurs of monosaccharides, they are unable to cross the cell membrane, and that's why they are not released from the cell. Understand? So generally, phosphorylated carbohydrates are present mainly in the cytoplasm. Understood? Now we come to the pentose, because pentose is not important for us. Ribose. Ribose is a How many carbons are present in ribose? 5 carbon. It means it is pentose. And functional group is aldehyde or ketone? Good. That is ribulose. When functional group is aldehyde, it is called ribose. When functional group is ketone, it is called ribulose. Okay? Is it? It is ribose. Okay. How many carbons are present? 1, 2, 3, 4, 5. 5 carbons are present. But how many carbons will be asymmetrical or asymmetric carbon or chiral carbon? Who will tell? Please raise your hand. Apurva, how many carbons in this are chiral or asymmetric? 3. No? So how many isomers you will get?
6.
Huh?
8. No? 2 to the power 3. 2 to the power n. So 2 into 2 into 2. Total 8. 8 isomers you will get from it. This is your ribose. If there is change at this, at the second carbon, this OH comes in the left and H goes in the right, then it is ribose. If at third carbon it changes, then it is xylose. If all the two, because at fourth position, one thing I mentioned earlier, if there is change at the penultimate carbon, change of the functional group at penultimate carbon, on that basis we call it D and F. Therefore this position you have not to change, because whatever I am mentioning, all these are D. D ribose, D mannose, D xylose, and one more. Actually, I perhaps put it there. D-lixose. D-lixose. You can see here. Ribose. Okay. Arabinose at the second carbon. OH is when third carbon. Xylose, and when second and third both, then lixose. Because at fourth carbon there will not be change. If it changes, then it will be alpha. So if you put ribose here and you change again the same thing, if you do so this is your D-ribose and this is your D-arabinose. And if it changes here, then it will be D-xylose, and if it changes at both positions, then D-lixose. And now you change at fourth position in each. Then how many isomers? At all the four, if you change, All these are D forms, 4 D forms, and if you change at this fourth position, then it will be L form of all. So how many isomers you will get? Thus you will get 8 isomers. Understand? Generally we make D form, as you know it is present in the nature. Generally L form is not present.
So according to organic chemistry, how do we number this
From the functional group.
from the functional group?
group side. So, now I am coming to hexose. In hexose, the same thing, 6 carbon. Sanjana, what is it?
H.
Yeah. Oh, sorry. H. Yeah. Now, what is it? What is it? On the basis of number of carbon, it is hexose because 6 carbons are present. But chemical name, its name is halose. What is it? Halose. Like that. If it changes at the second carbon, then it is aldose. If it changes at third carbon, then it is glucose. If it changes at fourth carbon, then it is glucose. If it changes at second and third, then it is mannose. If it changes at second and fourth, then it is second and fourth, then iodose. If it changes at third and fourth, then it is galactose. If all the three position, second, third and fourth, then it is tegatose. No, telose. Tegatose in keto form.
Can you please repeat?
I am explaining it. It is halose, okay, same 6 carbon. You have to change the position. Second carbon, the other one. It is aldose. If at this position, in this case, all hydrogen are in left and all hydroxyl in the right. In this, except at the second carbon, all are similar to halose. At the second carbon, OH is at the left side, OH is in the left side, and H is in the right side. Therefore, it is halose. If the same type of change occurs at the third carbon, then it is glucose. And at fourth carbon, glucose, G-U-L-O-S-E, glucose. Understand? And if it occurs at second and third carbon, then it is mannose. And if it at second and fourth carbon, then it is iodose. And if it is at third and fourth, then it is galactose. Now, one thing is here, if you make what is it? It is manoj. Now you see. What is it?
Hello, sir.
Oh, sorry. Now what is it? It is glucose, isn't it? Actually, you see, only at one carbon, that is adjacent, you take the position first, second, third, fourth, fifth, sixth. First, second, third, fourth, fifth, sixth. At third carbon, the structure of both are the same, but at the second carbon, mannose is different from glucose. If at adjacent carbon there is difference, so these are called epimers of one another. I will explain it. You may all know what I am using here. I will explain that. So on this way, how many isomers you will get? 16. Because how many? 1, 2, 3, 4. 4 carbons are chiral. So when you will put 2 to the power 4, so how many? 16. As I mentioned, allose, altrose, glucose, gulose, manoj, iodose, galactose, telose. How many? Total? 8. And if you change at this position, fifth position, these are D forms. And if you change at, then what will be? L form of each. So you will get 16.
So, my question is, how did they confirm that this is the position of OH?
Optical rotation,
Huh?
and plane polarized light, and that optical thing also, on that basis they have determined.
And D and L also is optical rotation.
These and all, that is plane polarized light when passes through the solution.
It rotates.
But when they have given some, that's nowadays they are checking the blood glucose level.
Yes.
So they oxidize glucose. There is a special strip in which there is glucose oxidase enzyme, and when blood is put on it, then there is oxidation of glucose, and then it gives a different type of color. It's metabolic. The same thing I mentioned earlier. When sorbitol is aided in the culture of bacterial culture. If there is infection of pathogenic E. coli, then it can be detected. So actually the metabolic activity becomes different, and with the help of a spectrophotometer.
So these are all naturally occurring hexoses?
Yeah.
Huh?
Yeah. Actually, from
So,
different types
if
of
they are
plants.
occurring naturally, does each of these hexoses has its own enzyme?
No, for hexose there is no need of enzyme.
No, not hexose. I will say allose has its own enzyme
For what?
for doing some work.
No, actually
If
when it is utilized, such as as I mentioned, lixose. Lixose is ultra low energy. Ultra low energy For psychos, so for psychos, there is ultra low energy. There is no, it is not easily metabolized, and there is energy generation is very low. So energy generation will be high when particularly is hexose. Among hexose, most of the time glucose is utilized.
Correct. Why?
And for that there is hexokinase enzyme.
So hexokinase is more of a kinase thing, na?
For glucose, it phosphorylates glucose.
Phosphorylates glucose.
Then there is formation of glucose 6-phosphate. There is no initially fructose 6-phosphate. Because these enzymes are also a specific. Hexokinase is a specific for glucose. It cannot act with other hexogens.
So there is okay. Because my question is, you may think I'm crazy, but are they artificially created or are they really naturally occurring?
Naturally.
They are occurring naturally.
On different from where they have been extracted, on that basis they have named.
And as such, glucose as a molecule, there is no enzyme which will work and break it into two. Is there any enzyme like that?
Initially,
so if I break glucose into two molecules, if I
then
want
it breaks into glyceraldehyde and dihydroxyacetone.
so
It is broken down. Glucose is not broken down. Fructose 1,6-diphosphate is broken down.
so it is through one step.
So is it not bisphosphate?
What?
Fructose 1,6 bisphosphate.
Fructose 1,6?
Bisphosphate.
The both things, diphosphate or bisphosphate. What is the
Yeah,
difference?
by na.
Di means 2, di means 2.
Correct.
So then why don't we write it as
Something
bis?
different.
This is according to the position.
Huh?
So it's according to
This
the
and that are
position.
different.
You are telling what?
So bisphosphate.
Fructose? What?
1,6 bisphosphate.
1,6 bisphosphate or diphosphate. What is
Number of
difference?
the number is same, sir, but the naming is different.
Different,
The
yes.
meaning differs.
This means that it is the same groups are attached, and di means it can be two different groups which can be attached.
But in the case of glycolysis,
It is always
So like
bisphosphate.
2 phosphate groups are attached. So it's the same, it's the same group.
phosphate is different.
So there is some difference.
What is difference? Tell me.
Some
Yes, there is particularly in glycolysis is divided into two parts, isn't it? Prefatory phase and payoff phase. When there is action of hexokinase, then one ATP is utilized, and that is hydrolyzed into ADP and inorganic phosphate. The same case occurs with fructose 6 phosphatase, na? And then fructokinase. Fructokinase, when fructokinase acts, phosphofructokinase. When phosphofructokinase acts at the same time, at that time also, there is a hydrolysis of ATP, and there is a generation of ADP and one molecule of inorganic phosphate, and it binds at first position of the fructose. What is difference? I will check.
The difference is that, like, if it's a diphosphate, then a whole molecule phosphate will be at different positions. But for a bisphosphate, it will be on the same atom. Like, if a single carbon is
1
there,
minute.
two.
I make it
phosphates.
nuclei. This is your first carbon. One phosphate is attached here, and one phosphate is attached here. What is difference? When your phosphate has 3PO4, P double bond O, single bond OH, single bond OH, single bond OH. One will bind here, And the same thing you will put it here. So what is difference?
So when it is bisphosphate, that means at two different positions the phosphate is adding, and if it is diphosphate,
No, what I am asking, what different position means what?
one is at one first position,
Carbon.
1,6. That is why we are specifying
One-
1,6 bisphosphate.
Uh-huh.
And if it is diphosphate, we do not specify the positions because it is understood that it's the
Single
same
molecule.
atom that the two phosphates are being
Single atom.
added to.
No, if we mention the position,
Then it's bisphosphate.
Bisphosphate, yes.
Is there any other position where phosphate can bind?
That's why we are
In different-
specifying the 1,6 bisphosphate. We
To
are not
specify the
talking
positions.
diphosphate.
If it's
Okay, I
diphosphate,
will
then
check
it's the
it.
same atom.
actually I have whatever I have read. I have read 1,6 diphosphate in, from my childhood.
So no, there is an isomerization step during
Fructose
the
isomer
Huh?
glycolysis.
That is different thing. When
There is
then
a step at the
in the case of it is escaping from my mind. That is a special case where 2,3 biphosphate, no? Bisphosphate is used when there's further 2,3 glyceraldehyde. Bisphosphate is also in a metabolic intermediate product.
So
In
that
that
is
case,
later on.
later
So
on.
this is in the
Ah.
The
previous.
nomenclature is this way, so whenever we have two
Okay, I will check
phosphates.
it. I will check it. Tomorrow we will discuss on it. Now, monosaccharides. Actually, mutarotation, as I mentioned earlier, when there is change in the position, at the 5th carbon, this is our which glucose? D glucose. Right? D glucose. And if at 5th position or 5th carbon, if the position becomes opposite, then it is, now it is L glucose. L glucose. But when it is in the ring form, particularly there is change at the first this is alpha D glucose. This is alpha D glucose, isn't it? But if the position becomes opposite, then it becomes theta D glucose. If we changes it here, then beta L glucose. Understand? So this rotation is called change in the optical rotation. Example, and alpha and beta anomers of D glucose interconvert in aqueous solution. When it is dissolved in water, and there is solution of glucose, particularly 64% of the solution contains beta glucose. As I mentioned, L glucose is not common in nature. Generally, D. And beta form is more common. When it is dissolved in water, then 64% is beta D glucose and 36% is alpha D glucose. Actually, due to this, when you considered in the space arrangement of atoms of the molecule, then particularly this position is closer to this, and that's why, and actually it comes here, this and this both repulses it, and that's why this, it is high energy state. Alpha form is high energy state, and it does not continue, it cannot continue for a longer period. That's why when it is dissolved, particularly it goes in the beta form to go in the low energy state. Now, anomers. Isomeric forms of monosaccharides that differ only in their configuration about the hemiacetal or hemiketal carbon atoms. Actually, hemiacetal and hemiketal, the fifth position, if you take beta, G form, here there is a reaction at the, this is aldehyde group and this is hydroxyl group. Actually, you can ask a question, but I will not make it clear because I don't know. I searched it, but I did not get its exact answer. When there is this open chain is converted into ring form, open chain is converted into ring form, at that time aldehyde functional group is present at first position and OH of fifth position takes part in reaction, and then due to this aldehyde and alcohol, now OH is functional group for alcohol, aldehyde and alcohol reaction, there is formation of hemiacetal. Hemiacetal, actually during hemiacetal, what is there is a rearrangement of molecules and there is shifting of hydrogen. You can see this hydrogen is shifted. This hydrogen is shifted, and due to shifting of this hydrogen from here, whatever structure initially develops here, it is called hemiacetal. The same thing, if it is in the ketone form, so in the ketone, the functional group is, if we take D, right, D fructose. This is your fructose. In the case of fructose, this fifth hydroxyl group at fifth position reacts with ketone group, ketone functional group, and here there is formation of hemiketone.